This video is for class 9 physics, and today we are doing some terms related to the wave motion. The first one being amplitude. So when a wave passes through a medium, the maximum displacement of the particle of a medium on the either side of its mean position is called the amplitude of the wave. So now here, whenever a wave is passing, from the previous video you must have known that either a compression is created or a rarefaction is created, then either crest is created or a trough is created. So when these things are being created, obviously the molecules need to move. So the maximum displacement of the molecule, right, either while creating a compression, either while creating a rarefactions, or while creating a crest, or while creating a trough, okay, the maximum displacement, right, is known as the amplitude, which is denoted by the small letter a, and the SI unit is meter. The next one is the time period. Here, time period, the time taken by a particle of a medium to complete its one vibration is called the time period of a wave. So now they are saying us the time taken by a particle means molecule of a medium, to complete its one vibration, means to come to the crest position and then come back to the trough position, or come to the compression position and then go back to the rarefaction position, right, and then come back to its mean position as well, right. So it will take some time, and that particular time will be known as actually time period. It is denoted by the letter T. The SI unit is seconds. Okay, further explaining this particular term time period, you can take an example of a simple pendulum. Okay, suppose the pendulum starts from the mean position, it goes to the left hand side, suppose, and it reaches an extreme position. Again it needs to come back to the mean position and then go to the right hand side's mean position. So once it comes back again to the mean position, at that time one complete oscillation is done. Now similarly, when the molecules in the medium vibrates in such a way that it goes to one extreme position and comes back to the mean position, again goes to the another extreme position, again comes back to the mean position, thus at that particular motion of the particle or the molecule in the medium, it needs to take some time, and that particular time is known as time period, or in simple words, time taken to make one wave, right, because we haven't discussed how much is one wave, therefore they are giving the definition in terms of the motion of the particles. Going to the next thing, which is frequency. Now frequency is the number of vibrations made by a particle in a medium in 1 second, right. Suppose it makes 40 vibrations in 1 second, then the frequency becomes 40. Is the same as the number of waves passing through a point in one in 1 second, right. It is denoted by the letters small f, n, or mu, right, or sorry, nu. Its SI unit is per second or hertz, right. The symbol the frequency f and the time period t are related as f equals to 1 upon t. The frequency of a wave is equal to the frequency of vibration of its source. That means if the pendulum is vibrating, oscillating, and it is producing sound, suppose, right, then the pendulum will also has frequency, the number of oscillation made in 1 second. The frequency of that pendulum will match with the frequency of the wave which it produces. It is the characteristics of its source which produces the disturbance. That means this frequency depends upon the source, the object which is vibrating. It does not depend on the amplitude of the vibration or on the nature of the medium in which the wave propagates. So it only depends upon the source, right. The frequency only depends upon the source. The next one is the wavelength. The distance traveled by the wave in one time period of a vibration of a particle of the medium is called the wavelength. So actually is the length of a given one wave, right. From the word only, wavelength is the length of a given wave. So length of a given wave can be there can be three ways to measure the length of a wave. The length of a wave can be measured between two consecutive compressions, or two consecutive rarefactions, or two consecutive mean positions, right. It is denoted by the letter lambda. Its SI unit is meter, and it depends on the medium in which the wave travels. So wavelength depends upon the medium, whereas the frequency does not depend upon the medium. Okay, here they are saying us the frequency does not depend upon the amplitude of vibration or on the nature of the medium, but wavelength, it depends on the medium, right, in which the wave travels. Next thing is, in a longitudinal wave, the distance between two consecutive compressions, here so many compressions were created, the distance between two consecutive compressions or between two consecutive rear fractions is equal to one wavelength, while in a transverse wave the distance between two consecutive crests or two consecutive troughs is equal to one wavelength. So let us try to understand with the figure only. We have come to the figure to understand the wavelength. Okay, the wavelength is the distance between two consecutive crests, any two consecutive crests, right, between these two crests. So this will be my wavelength denoted by lambda, or it can be the distance between two consecutive trough. Here it is the same distance, or which is not mentioned in the book, it can be the distance between the starting point of the wave, right, to make one crest and then one trough and ends here. So this particular length, okay, from this point to this point will be also my wavelength, in case of transverse wave. So let us try to understand for longitudinal wave as well. We have come to the longitudinal wave. These are the compressions, right, and these are the rear fractions. So the distance between two consecutive compression is a wavelength of this particular wave, or the distance between two consecutive rear fractions can be also considered as a wavelength, whose SI unit is meter. So I hope you have understood the wavelength. Okay, now let us go to the next topic, which is wave velocity. Wave velocity, the distance traveled by a wave in 1 second is called its wave velocity or wave speed. As we have already understood wavelength, okay, suppose the wavelength of a wave is 40 meter, and suppose it is produced in 1 second, suppose the time period is 1 second, then the wave velocity or the wave speed of that particular wave will be 40 meter per second. It is the speed with which the energy is transferred from one place to the another place by the wave motion. It is not the velocity of the individual particle. The particles were vibrating, if you remember. It is not the speed or the velocity of that particle, okay, which is vibrating about its mean position to form the crest, trough, or compressions and rear fractions, right? It is not the velocity of those particles which are moving. Rather, it is the velocity or the speed of the disturbance which is moving in the medium. It is denoted by the letter V. Its SI unit is meter per second, right? It may be noted that the wave velocity is the constant for a given medium. It depends on the elasticity and the density of the medium. It can change, it will change when the wave passes from one medium to the another medium. The next topic is a displacement time graph. Figure 8.8 shows the variation of the displacement time for a particle of a medium at a given position. So when a wave propagates through a medium, right, so here what they are trying to say is that we are trying to draw a graph, okay, of the displacement of the particles, not the wave, displacement of the particles with the time. Okay, so the variation of the displacement with time for a particle, for a given particle, only one particle of the medium at a given position. So when a wave propagates through the medium, it is called displacement time graph. In figure 8.8, the amplitude is represented by a letter A and the time period is represented by a letter T. Note that each particle of the medium goes through such motion, not simultaneously, but one after another as the wave moves in the medium. So let us go to that figure 8.8. Okay, so here is the figure 8.8 which shows the displacement time graph of particle of a wave. So this is the nature of the graph. This is the nature of the graph, not the wave. Okay, so here we are trying to make a displacement time graph for a wave. the wave can be transverse wave or the wave can be a longitudinal wave. Let's try to understand this by drawing the graph, by learning how to draw the graph, so that your confusions will be clear. So we can draw a graph. Okay, we are trying to draw one displacement time graph. Okay, so to draw a graph, as you all know, we need this. Sorry, I'm not using a ruler, so probably my line will be not so straight. Please bear with that. So this will be my x-axis, and this, sorry, that will be my y-axis. Sorry, y-axis, positive y-axis and negative y-axis, and this shall be my x-axis, and this is the origin of the graph. So I am supposed to draw a graph for a given wave. Okay, now let us consider a transverse wave. Let us consider a transverse wave. So this is a transverse wave, such that the particles here, I have shown the particles. I can change the color. Sorry, here. Suppose this is the particle, the blue ones is the particle. Here the particles is showing the maximum displacement. This is on the upper side and this is on the lower side. Okay, thus forming a crest and a trough. So this we need to represent in the form of graph. So suppose the wave starts from this position here, right, and suppose it starts at 0 seconds. So at 10 seconds it forms a crest. Again at 20 seconds, sorry, at 20 seconds it is coming back to the mean position. Then again at 30 seconds it is forming a trough. 40 seconds again coming back to the mean position. So we are getting a wave, right? So now this we need to represent in the form of graph. Thus to represent it in the graph, so this 0 denotes origin, so 10, then we have 20, 30, 40, 50, right? So what happened was the particle started from the origin, right, and at 10 seconds it reached a maximum position, suppose this, right, and then again at 20 seconds it came back to the mean position. Okay, so again this was denoted by the crest, right? Here this is not the crest, sorry, I can rub this. Okay, this is not the crest. So this represents the maximum position, the maximum displacement of the particle, displacement, right? So this is the displacement of the particle on one side, and then after 20 seconds it starts moving towards the other point, and at 30 seconds it reaches the lower most point, and then again comes back to the mean position, and the motion continues, right? And the motion continues. So here we can have another one. Okay, and similarly we can have another one. So it keeps on going. Okay, so we can have this in the form of graph. Remember, this is not the wave, this is the form of graph, although it looks like a transverse wave. So the question arises, can we draw the same kind of graph for the longitudinal wave? Okay, but before drawing the same kind of graph for the longitudinal wave, let us see what can we calculate. So here this denotes the distance. Okay, the distance suppose is measured in meter, right, and this particular x-axis denotes time, right, which is measured in seconds. So here the distance between the mean position, the origin, that is the x-axis, right, to the extreme position here, this is the amplitude A, because it is displacement along the y-axis, right, and along the x-axis we are measuring time. So therefore the length from this here, one crest I can say, to the other crest here, this distance, right, along the x-axis we are measuring time. So hence this can be denoted by the time period t. This can be denoted by the time period t, or we can start from this position here till the other trough or the other valley, right? So this is also one time period. Or you can measure it from here, this point, till this point. Okay, one wave, as I have shown, one wave, this is the single wave, sorry, not this point, sorry, not this point, okay, not this point, till one wave is over, till here, sorry, here, right? So yeah, so every time the value should be same. Let's see, here the value is from 0 to 40, so 40 seconds. Here is 50 minus 10, which is also 40 seconds. Let's see here, from 30 to 50, 60, 70, again 70 minus 30 shall give me 40. So every time the time period is coming same. Either you start measuring from the origin, or you start measuring from one crest to the another crest, or you start measuring from one trough to the another trough, the value is coming same, right? So this is for a given medium, right? So I hope you have understood the graph. From the graph we can calculate the time period t, right? And we can calculate the amplitude A, etc. So now let us try to draw the same kind of graph for the longitudinal wave. So we have come back to the longitudinal wave. Here we have compressions, rarefactions, etc. So now these compressions can be taken as a region of high pressure, right? And the rarefactions can be taken as a region of low pressure. Again the compressions high pressure, again the rarefactions low pressure, right? So we are getting a kind of wave, the shape is coming, right? But let us try to understand the displacement time graph. Now for the formation of these compressions and rarefactions also it's taking time. Suppose the wave starts at 0 seconds, right? After 10 seconds the compressions are being formed, okay, the topmost position. Then slowly the rarefactions will be formed at suppose 20 seconds. The wave comes back here at 20 seconds, right? And then we have rarefactions suppose in 30 seconds. Again the wave comes here at the mean position, so this will be the mean position of the wave here. Suppose here at this position, suppose it is at 40 seconds, and it keeps on going, right? So the mean position of the particle, actual mean position of the particle, is actually this particular mean positions, right? These red lines which I am drawing, okay, that is for the wave. But to draw the graph, okay, I am talking about to draw the graph. So now let us try to plot the graph. Okay, now I hope you have understood. Okay, this can be taken, I am just telling this can be taken, right? But the mean position is here. So if you want to understand more, okay, now what happens is when the particles are moving towards each other, okay, now this is the compression region, right? So when the particles are moving, so maximum, suppose a particle is here, suppose it has moved maximum here, right? So that can be shown by the upper part in one particular direction. Now what happens, the direction changes. In case of rarefactions, the particles are going back to its normal position. Suppose this particle is going back to its normal position. When the rarefaction in this region is created, then what happens is, okay, suppose this is the maximum displacement, but in the opposite direction. So to draw the graph, we need to show it in the opposite direction, that is in the negative direction. Suppose this is positive y-axis, so this will be negative y-axis because it is in the opposite direction, right? And the time is already here. So I hope you have understood how can we draw the graph, okay, for the longitudinal wave as well. So obviously we shall get the same kind of graph like this before, okay, the displacement time graph for longitudinal wave, okay. This is for the formation of one of the compressions, and then this is for the formation when the particles go back. This is for the formation of the rarefactions, so the compressions, rarefactions, compressions, rarefactions, and it continues, right? So we can get the same kind of graph. So this will represent the A, that is the amplitude, okay, amplitude, right? And whereas the distance, okay, if you want to continue with the graph, right, we'll have this kind of graph. The distance between these two hills will be shall be the time period, because we are measuring time along the x-axis. So I hope you have understood the graph. Okay, now let us go to the next type of graph, which is displacement distance graph. Now coming to the displacement distance graph, along the x-axis now we are taking distance, right, distance of covered by the wave. In figure 8.9 shows the displacement distance graph for a transverse wave at an instant. Here amplitude of a particles of the wave is shown by the letter a and the wavelength is shown by the letter lambda. The curve shows the displacement positions of the particles of the medium from their mean positions at an instant when wave propagates through the medium. It is also called a snapshot of a wave. That means this is a general wave. Okay, this is a general kind of a wave. Okay, so actually it's a sinusoidal wave. The wave can be of any shape. Okay, actually a triangular wave or square wave or rectangular wave, right? So we have a displacement distance graph here along the x-axis. Remember, now we are measuring the distance. Okay, so here we'll have the same kind of graph, because again the displacement is of the molecules of the particles which are moving up and down, since we are talking about the transverse wave, right? So this is the amplitude, that is the maximum displacement of a particle shown in the graph along the y-axis, and along the x-axis the graph proceeds further, right? So what happens is the distance now between the starting point of the graph and the formation of one heel, right, when the particle is moving in one direction and then particles returns back to the original mean position, right? So the distance from here to here can be considered as the wavelength of the graph, or the wavelength of the wave, or it can be between two consecutive crest, right, or two consecutive trough. So I hope you have understood the graph, or it can be between two consecutive troughs. The trough is not shown. Okay, if we continue the graph, we'll have a trough also, so this will also be a wavelength. So I hope you have understood till here, right? Then we can go to the relationship between the wavelength, wave velocity and frequency, right? So this is quite easy now. The wavelength, from the definition, which is the distance traveled by the wave in one time period or t seconds, right? Then wave velocity, that will be wave velocity into time period. So here to explain this, okay, you need to know the definition of wavelength. Okay, wavelength is the distance traveled by the wave between two consecutive crest or two consecutive trough, and the wave velocity was the distance traveled by the wave in 1 second, right? So from the formula of velocity, which is v equals to distance by time, right, here the wave velocity will be equal to distance is actually the wavelength and time is actually the time period. So by cross multiplying we shall get v into t equals to lambda, or I can say the product of the velocity or the wave velocity in the time period should give me the wavelength. And as you all know, the time period is the reciprocal of the frequency. Therefore we can write velocity, that is the wave velocity, equals to frequency multiplied by wavelength, because the time period is what, 1 upon f. So I hope you have understood till here, right? So we can write wave velocity equals to frequency into wavelength. This is another formula. So this much for this video. Thank you so much.